What happens when a Russian fuel train is destroyed in under 60 seconds?
At 6:05 a.m., 4 Ukrainian drones lifted off from a forest roughly 8 kilometers behind the front line. For a few seconds, they moved in silence, low altitude, stable formation, heading southwest toward their target. Then, their control systems activated. 4 signals burst into the air, hopping rapidly across frequencies between 1.1 and 1.5 gigahertzes, switching nearly 1,000 times per second. Invisible to the naked eye, but not to the system's listening. About 40 kilometers to the north, a Russian electronic surveillance vehicle detected the signals in under 0.25 seconds. Within another second, a second station, positioned approximately 45 kilometers away, picked up the same emissions from a different angle. The system compared the signal pattern's frequency range, hopping behavior, transmission power around 9 to 11 watts, and classified them as hostile drones. This wasn't guesswork. It was automated. The signals traveled at the speed of light, reaching one receiver just fractions of a microsecond before the other. The time difference, around 0.00008 seconds, translated into a positional offset of roughly 23 to 25 kilometers. The system plotted a curve, intersected it with the bearing lines, and locked onto a single point, the launch site. Total time from detection to confirmed coordinates, just over 20 seconds. No radar, no visual confirmation, just raw data turned into a precise location. Back in the forest, the Ukrainian operators continued guiding their drones, focused on maintaining course and altitude. They had no indication anything was wrong, but their position was no longer hidden. Coordinates had already been transmitted across the network. Fire control systems were receiving data. Launch units were beginning to align. The drones were still climbing. The operators were still in place. And somewhere, beyond their awareness, a response was already being prepared. At 6:23 a.m., roughly 30 kilometers away, a rocket artillery unit received the coordinates. The system didn't wait for confirmation. It didn't ask questions. It calculated, aligned, and prepared to fire within seconds. Launch tubes elevated to just over 50 degrees. Wind correction applied about 7 knots from the west. Target grid locked. One rocket ignited, then another, then a full ripple. Nearly 40 rockets tore into the sky in rapid succession, each traveling close to 700 meters per second. Their trajectory formed a wide arc over the battlefield, all converging toward a single grid roughly 500 meters across. Back in the forest, the Ukrainian team heard it instantly. Not a sharp blast, but a deep, rising roar that spread across the sky. They recognized it immediately. Impact was less than a minute away, but they couldn't move. Not yet. The drones were still under manual control, climbing past 1,300 meters and still short of the programmed handover point. Cutting the signal too early meant losing navigation, losing alignment, losing the entire mission. The sound intensified, splitting into multiple incoming trails, each one closing distance at lethal speed. The air itself seemed to vibrate as the rockets approached. Inside the control unit, the systems began to shift. The drones reached the handover zone. Autonomous navigation engaged. The team leader cut the control instantly, no countdown, no hesitation. Both operators moved at the same time, abandoning the control position and diving into their vehicle. The engine was already running. Tires spun hard against the dirt as they accelerated away from the launch site. A chain of explosions rolled across the forest behind them, wave after wave, saturating the entire grid. The blast front expanded outward, slamming into their vehicle at close to 200 meters. Fragments ripped through the rear panels, tearing metal and glass, but the vehicle kept moving. They survived the strike. Behind them, the launch site was erased. Ahead of them, the drones continued alone, following pre-programmed paths deeper into contested airspace. And this time, survival wouldn't depend on speed. It would depend on whether those drones could outthink the next layer of defense waiting ahead. At 6:45 a.m., the first response came from a Pantsir S-1 air defense system near the depot. Radar locked onto multiple incoming drones, fast, low, and approaching from different altitudes. The operator reacted immediately. 2 missiles launched toward the highest drone. Another pair followed toward a second target. Each interceptor moved at nearly 800 meters per second. Both drones were destroyed mid-air. For a moment, the sky cleared, but those were not the real strike units. They were decoys flying higher, easier to detect, designed to trigger an early response. While the Pantsir engaged them, the actual attack remained low, below radar priority, harder to track. By the time the system shifted focus, the surviving drone had already slipped through. It approached the fuel train at high speed, nearly 70 meters per second. Tanker cars were lined across the rail, each carrying around 55 to 60 tons of diesel. The drone struck directly into a central tanker car. The explosion tore through the steel shell, sending burning fuel outward across the tracks. Fire spread immediately to nearby cars, igniting additional fuel within seconds. Heat built rapidly. Pressure valves released vapor, feeding the flames and expanding the fire along the train. Then came the second drone. It emerged through the smoke from a different direction, aligned with the wind. It ignored the burning train and locked onto the fuel transfer structure behind it. The blast ruptured internal storage tanks, releasing a dense fuel-air mixture that ignited instantly. A powerful shockwave spread across the depot, amplifying the fire from the train and engulfing the surrounding area. Within less than a minute, the entire fuel operation was disabled. The Pantsir S1 reacted fast, but the attack was designed to make it react first and react wrong. The second explosion did not end the attack. When the drone struck the fuel transfer building, the detonation ruptured multiple storage tanks at once. Inside, a dense mix of fuel vapor and air formed instantly, then ignited. The secondary blast was significantly stronger than the first, sending a pressure wave across the entire depot. Metal frames bent, roof sections collapsed, fuel lines snapped, temperatures surged past 700 to 900 degrees Celsius within seconds. Outside, the fire from the train had already spread. Several tanker cars, each carrying close to 55 tons of diesel, were now fully burning. Fuel leaked onto the tracks, creating continuous lines of fire that connected one car to another. Then the chain reaction began. Heat triggered pressure valves on nearby tankers. Vapor released directly into the flames, increasing intensity. One tanker failed structurally, its shell weakening under heat before collapsing and feeding even more fuel into the fire. Within less than a minute, over 250 to 300 tons of fuel were actively burning. The depot was no longer a controlled environment. It was a continuous fire zone. Flames spread across rail lines, engulfing additional cars and reaching nearby infrastructure. Thick black smoke rose rapidly, visible from more than 5 kilometers away. The shockwave from the second blast had already damaged structures across a wide radius. Inside the depot, all operations stopped. Pumping systems failed, transfer lines were destroyed, power was cut. The connection between train and storage was completely broken. There was no immediate way to contain the fire. Heat levels made it impossible for response teams to approach the center. Visibility dropped as smoke and heat distortion covered the entire area. The damage was not just physical, it was systemic. The depot had been a key supply point. Fuel moving through this location supported multiple downstream units. With the transfer system destroyed, that entire flow was interrupted. All of it triggered in under a minute. 2 drones, 2 impacts, and a chain reaction that shut down an entire fuel operation. The strike was complete, but the disruption had only started. Long before the explosions at 6:45, the real breakthrough had already happened. At around 6:18, the remaining 2 drones dropped lower, far lower than standard flight profiles. Altitude decreased to nearly 40-60 meters above ground, forcing them into the terrain itself. Hills, shallow valleys, and even rail embankments became cover. From above, radar could still see them, but from the side where it mattered most, they began to disappear. The curvature of the Earth, combined with uneven terrain, created blind zones. At distances beyond 20 kilometers, even a slight dip in elevation could produce a radar shadow of over 35 meters. Enough to break a tracking lock, and that's exactly what happened. The air defense system attempted to maintain contact, but the signals weakened, flickering in and out. Every time a drone dropped behind terrain, the radar lost continuity. Reacquiring the target took time the drones used to move closer. By the time the system repositioned, lowering radar, adjusting angle, stabilizing again, the drones had already advanced nearly 10 to 12 kilometers. Then came the second barrier. At approximately 6:35, both drones entered a heavy electronic warfare zone. A jamming system near the depot activated at full power, broadcasting noise across GPS frequencies at nearly 100 watts. Compared to satellite signals, which arrive extremely weak after traveling 20,000 kilometers, the interference was overwhelming. GPS dropped instantly. Positioning systems failed. The drones switched to inertial navigation using internal sensors to estimate direction and movement. But this method wasn't perfect. Error accumulated quickly around 10 meters per minute. sometimes more under unstable conditions. At the same time, the video link degraded. Frame rate dropped, signal lag increased to nearly half a second. Visual clarity collapsed into fragments. But control wasn't lost. The drone antennas, pointed back toward the operators, amplified the remaining signal. Even with over 80% packet loss, enough data passed through to maintain limited control. Operators adapted. They lowered resolution, reduced frame load, prioritized response speed over image quality. The drones continued forward not with perfect precision, but with just enough control to stay on course. This was no longer about technology alone. It was about persistence under degradation. By the time the drones exited the worst of the interference, they were already within striking distance. The defenses had tried to blind them. But the drones didn't need perfect vision. They only needed enough to finish the path. By 6:42 a.m., the drones were no longer navigating by maps. They were navigating by heat. Through interference and signal loss, the onboard cameras switched to thermal mode. The landscape below faded into darkness, but the depot stood out bright, defined, impossible to miss. Metal retained heat from the previous day, and the long line of tanker cars appeared as glowing rectangles stretching across the rail line. Two parallel lines of heat, the tracks pointed directly to the target. Distance, just under 5 kilometers. Time to impact, less than 2 minutes. The jamming system was still active, pushing noise across multiple frequency bands. Signal delay fluctuated between 300 and 500 milliseconds. Video feed dropped to under 10 frames per second. Every movement came with lag. Every correction arrived late. But it was enough. The first drone adjusted slightly, just a few degrees, to align with the center of the formation. Altitude dropped steadily to around 300 meters. Speed increased. Below, the depot continued operating. Fuel transfer was still in progress. Pumps were active, valves open. No indication that an attack had already penetrated the outer defenses. Then, the final approach began. The drone accelerated into a direct path toward the train. No evasive movement, no deviation. The warhead detonated instantly on contact, releasing a high-pressure blast that exceeded the tanker's structural limits several times over. The outer shell ruptured immediately. Fuel sprayed outward and ignited, forming a rapidly expanding fire zone. Heat spread across adjacent cars within seconds. The second drone followed closely behind, but it did not target the train. Through the thermal haze, it identified a larger structure beyond the fuel transfer building. Its outline appeared as a dense, rectangular heat signature, connected to the rail system by multiple pipelines. The drone climbed briefly to around 300 and 400 meters, then entered a steep descent. Signal lag increased. Video froze momentarily, then returned. Alignment held. Impact. The explosion inside the structure triggered a confined fuel-air ignition, amplifying the blast far beyond the initial detonation. Pressure surged outward, rupturing additional storage tanks and sending a shockwave across the depot. Within seconds, multiple fire sources merged: train, transfer lines, storage, facility. All connected, all burning. The attack sequence from first strike to final detonation took less than 90 seconds. There was no follow-up. No second wave. There didn't need to be. The system had already collapsed from within. In less than 1 minute, the target was gone. A fuel train carrying hundreds of tons of diesel, disabled. A transfer depot designed to supply entire sectors, shut down. Not by missiles, not by large-scale bombardment, but by just a few drones. And that's what makes this story different, because this wasn't about firepower, it was about timing. Every layer of defense worked exactly as designed. The signals were detected, the coordinates were calculated, rockets were launched, air defense systems engaged, jamming systems activated. Nothing failed. And yet, the mission still succeeded. Because the attack was never about breaking the system, it was about understanding it. The drones that were destroyed weren't losses, they were part of the plan. The signals that gave away the operators weren't mistakes, they triggered the response. Every reaction from the defense created a new opening. Step by step, layer by layer, the system was forced to do exactly what it was built to do, and in doing so, it exposed its own limits. What you've just seen isn't just a drone strike. It's a new kind of battlefield logic where small, low-cost systems can create disproportionate effects, not through brute force, but through precision and strategy. The real damage isn't just the fire you see, it's the disruption that follows. Fuel doesn't arrive, vehicles don't move, operations slow down, and all of it starts from a single moment when a signal is detected. So here's the question: if you were designing that defense system, what would you change after watching this? And if you were the one planning the attack, would you rely on speed or on making your enemy react exactly the way you want? Because in modern warfare, the side that wins isn't always the one with more power. It's the one that understands the system better than anyone else.